2.12. Thanks, George.
Second one is 7.21. And the third one is 2.32.
You gotta be higher than that. 12.32? Okay, so let's go to our titration curve. So let's see. At the first halfway point, the pH is going to equal 2.12. At the second halfway point, the pH is going to equal 7.21. At the first end point, that's going to be the average of these two numbers. So that's going to be, let's see, 9.33 divided by 2, or 4.66. Okay. pH 3 is right in here. So at pH 3, what phosphorus-containing substances are going to be present? Yeah, so at pH 3, we're going to have the H3PO4 present, and then we're also going to have H2PO4 minus, and then which one's going to be the acid? Yeah, so this is our acid, and then this is the base. Now, if the pH is around 7, what substances would be present? Yeah, so we're going to look at this equilibrium reaction, the H2PO4 minus as the acid and the HPO42 minus as the base. And then note also, since we were talking about charge, the charge changes. So at pH 3, we're going to have part of that solution has 0 charge, the other part has a -1 charge. Okay, part B, calculate the ratio of these phosphorus-containing substances in Coca-Cola at pH 3. So the equation you want to use to answer question B is that Henderson-Hasselbalch equation. Okay, so this equation states that pH is equal to pKa plus the log of the base divided by the acid, the H2PO4 minus to the H3PO4. So let's plug in our numbers. So this is going to be 3 is equal to 2.12. Okay, so then we can just solve for this ratio. So if we solve for that ratio, we have H2PO4 divided by H3PO4, and that's equal to 10 to the 0.88 power, 7.59. Yeah, this is the ratio between those two. So we'll have 7.59 of the base to 1 of the acid. So note that this titration curve is like walking up the steps of those big pyramids yeah, I don't know where. If you went to a pyramid during spring break, or walking up the steps from the beach to your villa on the beach during your spring break. Yeah, so note the other thing too about Coca-Cola is the pH is 3, and note that at that pH, it's actually going to also serve as a buffer. Now, did anyone watch 60 Minutes? Not this past weekend, but the weekend before. There was a segment on sugar, how sugar is bad for you, how sugar is turned into fat, and how us Americans eating too much sugar, and that's why we got this obesity problem. Yes, take a look at that, because there's the guy who's the researcher who is doing this kind of work works at UCSF, just up the road. Yeah, so take a look at that 60 Minutes segment. And then the other thing with these acidic foods is that it causes cavities in our teeth because the acid is going to okay, so we have our tooth enamel is this mineral called apatite. Is this compound here? Ca. Let's see. It's Ca. Let's see. I gotta think about it. Yeah, so this is the tooth enamel. Ca5PO4OH. That's tooth enamel. So note that we have a metal and then the phosphate and hydroxylase. So note that this is the basic part. So if this is the basic part, this is going to react with acids. So acid will actually dissolve tooth enamel. And when that happens, then it causes cavities. So it turns out that a lot of foods are acids, as we saw when we were looking at that web page. We showed the pH of various foods. So I hope none of you are those fluoride conspiracists, because it actually does help scientifically if you use fluoride. That's going to replace the OH with this compound, make this compound here. And this is actually resistant to acids, so that's how fluoride is supposed to work, to protect teeth from getting cavities.
So then if you have never had a cavity, and you could assume that your enamel is like strong, does that mean that you have that fluoride compound instead of it?
No, so well, I guess, if you've never had a cavity, that could mean that you or a person who's never had cavities has been either using fluoridated water or has been brushing with fluoride-containing toothpaste, which means that their teeth is strong. Yeah, fluoride, your enamel is strong. Now the other thing too about getting cavities is actually, there's this, for example, the sugar. If you eat too much sugar too, this is the other thing. The sugar feeds this bacteria, the bacteria in your teeth. Bacteria form on the enamel in your teeth, that causes cavities. See?
You know how you said that when you eat a lot of sugar, it can be more overweight? I don't know how much sugar fruit contains, but how come that, citrus fruits are really sweet? How come people who eat a lot of citrus fruits, they're not fat?
Oh, see, this is actually what this researcher is saying in the 60 Minutes segment. He says that, see, one problem with, say, with juice is that it's mainly all sugar. That's why he recommends drinking water and eating fruit, because not only does the fruit contain fruit sugar like fructose, but also contains fiber and vitamins and other things too. So he says that if you're gonna eat, get your sugar naturally from the foods, as opposed to artificially from drinking juices or and foods which have added sugar to it. So he said this is the other thing, because he thinks evolutionary. If you taste something which is bitter, that tells your brain that must be bad for you. You spit it out, no good. Whereas if you eat something sweet, it says, well, this must be good, and therefore you eat more of it. So, but then what this researcher is saying is that, well, it's not really true. Eating things which are sweet, which contain sugar, really isn't good for you because it turns into fat.
Is it because glucose is like fuel for our brain? Is that why like we like so?
Well, see, that's a good thing because, for example, in table sugar, sucrose, it contains, part of it is glucose, the other part is fructose. And then a lot of these corn syrups, like high fructose corn syrup, has a lot of fructose. And this guy's claiming that both sucrose and fructose are both bad for you. And he says that although the glucose is needed for the fuel in our body, we metabolize the glucose for energy.
And that's contained in fruit, right?
Yeah. Yeah, so although the glucose is what we need for the fuel, the fructose is what you don't actually. So the fructose, I think according to researchers, fructose goes to our liver, and in our liver it metabolizes. If we don't use it as fuel, it metabolizes into fat. Okay, you guys ready to start the second part of Chem1B? Okay. I'm not sure if I'm ready. I guess we'll go anyway. Okay, so let's go back and talk about energy. We know that every chemical reaction or physical process involves energy. So let's fill in the blank here. So energy is matter. Well, actually, we define scientifically matter is defined as something which has mass and occupies space. So, and we see what matter is. We can see it, for example, solids and liquids. We can measure it. We have instruments specifically designed to measure matter, mass and volume and things like that. But what about energy? So what would you put in that blank there?
Work.
Yeah, so energy is work.
Conserve.
Anything else?
Conserve. Energy is conserved.
Yeah, and you see we have those conservation laws. Yeah, conservation energy. Now work is a type. Are there any other types of energy besides work? This is one reason you're going to school, so you can work. Note that work either requires energy or I'm not sure if it releases energy. Unless you get so stressed out at work, then you do something. You go ballistic. You go postal. You don't want that kind of job. Okay, so there are any types of energy besides work and heat and potential energy and kinetic energy and electrical energy. Yes, there's all different types of energy. So going back to what we talked about earlier, we talked about reaction rates. Reaction rates tell us how fast or slow a reaction occurs. And as we discussed earlier, we know that there's three factors that determines reaction rate: concentration, temperature, and catalyst. Now in Chem1A, I'm not sure if you remember this, we said that energy also tells us whether a reaction occurs. So this is the topic of thermodynamics. Thermodynamics tells us, it talks about the reactants and the products, that is the initial state and the final state only. Okay, whereas reaction rates talk about what goes on in between the reactants and products. Going back to Chem1A, we said that there are two driving forces for a chemical reaction, and those two driving forces are enthalpy and entropy. So let's take a look at our reaction energy diagram again. So if you look at this diagram, Is this reaction fast or slow? Or I wanted to put a third choice, so I put good in there. So is it a good reaction?
It's good.
Fast or slow?
It's
Fast, slow, good. Yeah, there are good reactions and bad reactions. Like this reaction here may be considered a good reaction because it's protecting your teeth. The reaction of this with acid may be a bad reaction if you get to cavities. So, based on that reaction energy item, is this reaction fast or slow or good? Why is it fast? How do you know it's fast?
There's no activation.
Yeah, look at